name is Jiwu LEE from the KGSEA Math Circle, and today I will be discussing paradoxes, what they are, and several examples of them. So the most important question when discussing paradoxes is, what is a paradox? And there are many different definitions that one can come up with. However, the one I'll be using for the purpose of this lecture is, quote, a statement that is seemingly contradictory but also possibly true. This is a very vague definition, and it can be difficult to understand what a paradox is from just a statement. So as an example, here's one of the most basic examples of a paradox. This statement is a lie. This is a paradox as if the statement really is a lie. That would mean that the statement is a truth, meaning that the statement is a lie, meaning that the statement is a truth, and so on. So to actually dive into a more realistic example of a paradox, the Monty Hall problem is one of the most famous paradoxes. The premise is as follows. You're a participant in a game show and are given the option to choose between 3 doors, 2 with goats and 1 with a brand new car behind them. You are given the option to choose 1 door, and then after, the game show host opens one of the doors and reveals a goat. He then gives you the opportunity to switch. While it may seem that you have a 1/3 chance of choosing this car no matter what you do, so the switching doesn't matter, is actually the more beneficial option to switch doors. So this comes from the 3 standard assumptions that apply because of the condition that you are a part of a game show. The first is that the host cannot open the door with the car, which defeats the purpose of the show. The second is that the host knows the location of the car and that the host does not open the door that you are on. From this, we can assume that if you first chose door 1, we can make up 3 scenarios of where the cars are behind door 1, door 2, and door 3. From then, we can see what would happen if you switched doors, as for the first example where the car is behind door 3 and you're in front of door 1. The host would be forced to select door 2, as opening door 3 would reveal the car immediately. So switching doors would win you the car. This is the same case for the second option, but for the third option, since you're already behind the car, if you switch, you would lose the goat, and that is the only option where you would in fact lose from switching. Another paradox that I will be talking about is the unexpected hanging paradox, and this is what I'll define as a type of logical contradiction. The premise for this paradox is as follows. A death row inmate is told that they will be hanged on noon on a weekday the following week. He is also told that he will not expect this hanging. Using this, he deduces that he will not be hanged. If you want to give this problem a try, I'll give you 5 seconds. So the reason that the prisoner deduces that he will not be hanged is that if he is not hanged on Thursday noon, he knows that he will be hanged on Friday. And from that, he deduces that if he's not hanged on Wednesday noon, he will be hanged on Thursday, which means that it will not be unexpected, and he uses that logic to reason that he will not be hanged on a weekday. This is a paradox as it goes against the original claim that the prisoner will in fact be hanged. Next, I'll be covering 2 examples of mathematical paradoxes, the first being the 2-envelope problem. The premise for this paradox is that you are given 1 envelope, one with twice the money than the other, $10 in this case, and you choose one randomly. You're then given the option to switch. This is a problem very similar to the Monty Hall problem that I mentioned earlier. And again, one can make the assumption that there is no gain from switching. There are many ways to approach this problem where it could give both outcomes. The mathematical solution is as follows. Assume that the amount of money in the envelope you chose is X dollars. Then the amount of money in the other envelope will either be 2x or 1/2 X dollars. There is an equal probability of both with a 50% probability. So if we calculate the expected value, we would get 5/4x. Another way to approach the scenario is by considering that the total amount of money in both of the envelopes is X dollars. Using that, we can deduce that the smaller envelope will have X/3 while the envelope with more money would have 2/3 dollars. Using that, you will either be gaining 3/x dollars or you will be losing 3/x dollars by switching. So using that, if we calculate the expected value once again, we will get $0. Thus, this is an example of a quote-unquote solved paradox, which I'll be explaining. The second mathematical paradox I'll be discussing is the St. Petersburg paradox. This is also a paradox that involves expected value. The premise for this paradox is that your reward at the start is $1, and every time you flip a coin and correctly guess which side the coin lands on, you double your reward. And if you guess incorrectly, you take the money you earned. So if we calculate the expected value of this, we would get this equation as there's a 1/2 chance that you get $2 and 1 in 4 chance that you get $4 and so on. And that would equal to 1 plus 1 plus 1 plus so on, which is equal to infinity. This is a paradox on common sense, as while the expected value is infinite, meaning that most people would theoretically want to have to take any opportunity to play this game as they have the chance of winning infinite money, none would actually be willing to play this game for more than something like $10. And this paradox is due to the discrepancy in expected value and what people would actually pay to enter the game. The final category of paradoxes that I'll be discussing are philosophical paradoxes. These are paradoxes with no apparent answers to them. One of them is the ship of Theseus. This is also a pretty famous paradox, and it goes as follows. There's a very old ship, but as the parts of the ship wear down, it is replaced one by one over time. The question is that then is this ship still the same as the original ship, as all of the parts have been replaced, but have been replaced very slowly, meaning that they were still the same ship at one point. And the extended version of paradox is that if we use the original parts that we already replaced to make another ship, would that be an original ship? And if so, which would be the real ship? Another type of paradox with no real answer that I'll be discussing is the Fermi paradox. It simply states that if the universe is constantly expanding and that there are numerous stars and galaxies, why have there been no signs of alien civilizations? There are many proposed hypotheses and solutions to this problem, such as the dark forest solution, named after a book by the same name by Liu Cixin, which states that it is simply too dangerous to attempt to communicate with extraterrestrial species, or other solutions such as the fact that intelligent life may be too difficult to form, such as known as the Great Filter hypothesis, or another such that intelligent life is simply bound to destroy themselves and their own civilization. That will be it for this lecture.